Hi everyone, in this video I'm taking a look at question 14 part E of the 2020 Extension 2 trial exam from Sydney Boys High School, which is a selective school in Sydney. For this question we're told in the Argand diagram below, two concentric circles have radii of lowercase and uppercase r, and we're told that the lowercase r is less than the uppercase r. The center C of the two circles is represented by the complex number Ci. The largest circle touches the real axis only once, and that is at the origin. The chord OB is tangential to the smaller circle. OB makes an angle theta with the real axis. Other points are marked for convenience if necessary, and in general, BD, the line BD, is not parallel to the imaginary axis. So we can see in the diagram here it kind of looks parallel, but we're basically being told that isn't necessarily always going to be the case. I suppose it will depend where B is. So this question has two parts. I'll work through this part one in this video and then do a follow-up video for part two. Part one says, given that the equation of the region bounded by the two circles, inclusive of the circles, is r being less than the magnitude of z minus c, which is less than, so lowercase r less than the magnitude of z minus c, which is less than uppercase r, we're then asked to write an expression for the complex number at point B in terms of lowercase r, uppercase r, and theta in exponential form. So here we're in complex number territory, which hopefully is quite obvious given we're told we're dealing with an Argand diagram. But what we'll see as we work through both this part one and part two is really, I think the essence of it is actually trigonometry. We're making use of our knowledge of trigonometry and also circles in a way. And that is going to let us make conclusions about complex numbers. So yeah, let's take a look. So what I'll do to start is I'll try and recreate this diagram as best I can to make reference to it. So I'll get my handy electric soccer tape, which I found is the best way for me to draw circles that aren't totally wonky. So let's just, the beauty of this soccer tape is I can actually draw two concentric circles pretty easily because I've got the outside of the tape for one and then I've got the inside of the tape for the other. And whilst my diagram won't be perfectly the same as the one we saw in the question, I think it'll have everything we need. So maybe I'll just get my ruler and we'll call this the origin. So we've got the axes of our Argand plane. So this will be the imaginary axis. This will be the real axis. So just put our arrows here. So we've got our real axis. And so we're told that the center of the circle, and maybe if I try and get this somewhat right, let's measure this. What is this total circle? About 5.5, so maybe 2.75 or so. So that's going to be the center of both circles. So we'll call that C. We're told that there's a line that's tangential to the smaller circle. So say here, that point, and then we'll have this point. So the point that's tangential is called A. And then the point that hits the outer circle was called B. And then we've got this line, OB. And then there's also the line that I think they dotted in the diagram, which kind of went from the center of both circles out to the outer circle, and that was called point D. And then they also dotted the line between B and D, noting that it wasn't parallel to the imaginary axis, and in my diagram it clearly isn't, so it's almost more helpful in that regard. What else were we told? I think we were told that this angle, that the line OB mates with the real axis is theta, so that's obviously going to be very helpful when thinking about exponential form of complex numbers. And I'm pretty sure that's the key information. And in essence, for this part one, we're being asked to write the point B. What would point B be as a complex number in exponential form? And so if we go back to the basics of exponential form, we'll have the length or the modulus of the complex number times e to the power of I theta, where theta is our angle that the complex number makes with the real axis. So actually, if I just note it up here, we're basically going to have b, the complex number b, is equal to, I'll just write OB to represent the length of this line OB, times e to the I theta. That's our exponential form. Now, we were asked to show it in terms of lowercase r, uppercase r, and theta. Now, we've already got theta up here in our exponent, so that's job done pretty easy. So really the essence of this question is, how do we get the length of OB in terms of r, lowercase r, and uppercase r? And so that's basically, maybe I'll note that down. We need OB in terms of lowercase r and uppercase r. And I think if we can get that length, we can throw it into this and it's job done for part one. Okay, now let's start annotating onto this diagram the various things we can know from the information we're given. And I think maybe I'll use red. The first thing to note is that if OB is tangential to this circle, then this line here will be perpendicular. CD will be perpendicular to OB because a tangent will be perpendicular to the radius. So we can note that right there. Now, another thing we can note is that the length of OA will be equal to the length of AB. And that's making use of a result where a perpendicular radius, which we've got here, a perpendicular radius, will bisect a chord, and OB is a chord because both O and B lie on the circle. Now, I've actually got a little short video where I work through that proof, the proof of that result. So if it's not something you're familiar with, I'll provide a link to that little short video, and you can have a look. It's a very easy proof. It actually uses Pythagoras, and actually it wouldn't take a lot of effort if, for example, you were to just draw on this line here from C to B. You kind of know that the length from C to O is capital R, we're told. That's the radius of the outer circle. The length from C to B will also be capital R because that's also a radius. So we know this side and this side are equal. We also know that this side in both these triangles is equal because it's literally the same side. And so, you know, with not a lot of effort using Pythagoras, you'd work out that the length of each of these sides is also equal. So you could do the work to prove it, but actually in the context of this question, you could probably get away with just writing OA is equal to AB, since you'd write a perpendicular radius bisects a chord. And I think that would be enough to clearly show whoever's marking this that you understand. It wouldn't hurt to show the proof if you wanted, but hey, it's a timed exam. If you can save a few moments, it's always a good thing. So now, from there, we can actually say that this length OB, which is what we care about, remember that's what we're trying to find, that's actually just going to be equal to 2 times OA. And therefore, if we can find OA in terms of lowercase r and uppercase r, then we're looking good. And actually, we've got OC as capital R. Now we've got CA as lowercase r because that's the radius of the smaller circle. So if perhaps I'll redraw, I'll just draw this circle OCA, and I think we're going to have everything we need to do what we want to do. So let's draw up just this triangle separately so that we can annotate it clearly without all the other noise going on. So if I put the right angle here, so that would be point A. So we'd have point O here, and then point C as the final point. And we know OC is capital R. We know CA is lowercase r. And we're looking for OA because if we find OA, then we've got OB, and then we've got our complex number in exponential form. So now we can just say by Pythagoras, so again using some pretty basic trigonometry to get our complex number results, we can say that r squared, the hypotenuse squared, will be equal to the sum of the squares of the other two sides, so lowercase r squared plus OA squared. So let's isolate OA because that's what we care about. So we'll get OA squared equals, we'll subtract this over, so capital R squared minus lowercase r squared. And then we'll just take the square root. And we only need the positive square root because we're dealing with the length. So we'll get the positive square root of capital R squared minus lowercase r squared is OA. And so now we're good. So therefore, we can say OB is equal to 2 times OA, or 2 times the square root of capital R squared minus lowercase r squared. So therefore, the complex number B in exponential form is OB, so 2 times the square root of capital R squared minus lowercase r squared, e to the I theta.
Sonic boom!
And that's exactly what we needed to do. We've got our complex number in terms of lowercase r, uppercase R, and theta, and it's in exponential form. So yeah, that's all there is to that question. I think it's quite a daunting looking question with all these circles and triangles and all the terminology of the complex numbers being thrown around. But actually, if you take a look at this working, not a huge amount of working required to get to the result. So I suppose if you're thinking about this from an exam taking strategy perspective, it's really just another example where staying calm and kind of just trying to break things down calmly is often the way to go, because whilst it might look like at first glance a question is really trying to bamboozle you and throw a lot of stuff your way, often the way these questions are written, if they're written quite well, is that it just takes an application of some basic ideas to get to where you need to get to. So hopefully you found that explanation helpful for part 1. What we'll do now is we'll, in a follow-up video, I'm going to work through part 2. And as we see there, it's really just a lot more of the same. It's some more trigonometry being adopted to get some complex number results. All right, tick boom.